I got my data from the Global Terrorism Database from the University of Maryland. It's an open source database of unclassified terrorist attacks that are from 1970 to 2019. There's 200,000 observations and 135 variables that include anything from the description of the event, weapons used, the type of target, number of people killed, and sometimes the group and individual responsible if we know who they are. The original problem I wanted to address was what are the determinants of a high number of fatalities from a terrorist incident? This would be a regression problem, but as I dug into the variables, I realized that it requires a mix of continuous and categorical variables, and the continuous variables need to have normal distribution after transformation, which wasn't the case. So I switched to can we predict the attack type based on terrorist incident characteristics, where the target variable is attack type and it's a classification problem. I explored the continuous variables through box plots, histograms, frequency tables, and charts, and the categorical variables through frequency tables and charts, but also the multiple correspondence analysis. And this shows a plot of the target variable, which is the frequency of attack types. And you can see that the bombing explosion has the highest frequency. Box plots were used to help to identify the outliers in the continuous variables. The histograms were used for distribution, just to check it for normality. And the categorical variables, their frequency helped me determine which features to choose because ones that were imbalanced or had too few observations I didn't include. The continuous variables, which included the number of fatalities, casualties, and perpetrators, among others, needed two types of transformations. They needed normalization through the z-score method as well as a log transform. And if you look at this is a histogram of the terrorism fatalities variable. Even after the log transform, we don't have normal distribution, and this did not improve their skewness. And the categorical variables, on the other hand, needed one hot dummy encoding. After I found the outliers and removed them, I imputed missing data with means. And then I normalized and standardized the feature values. Here's the code. I used the function, which is the z-score method for normalization. And then I also did dummy codes for the categorical variables. So you can see here I created a new variable called Islamic group based on my knowledge about terrorism and some research. What would be some names that would fall into this category of the known perpetrators. And I also coded the region into one hot dummy variable of North America and Middle East and Africa. Finally, here's the log transform for those continuous variables and the histograms after the log transform, which did not improve. The models that I chose are naive Bayes, support vector machine, and the neural network ANN models. The reason I chose these models was because this is a classification problem which those algorithms can handle, and they don't require continuous variables the way that regression needs them in the mix, and they can also handle multi-level target variables. To run the models, I had to change all the variables that were chosen to factors, and then I chose to split the dataset 70-30 into a training and test dataset with replacement. How did the models perform? Here's the order of the algorithms from fastest to slowest. Naive Bayes was the best performer in terms of speed, and followed by the neural network. And then SVM took a little bit extra time because it doesn't handle larger data sets very well, and the more features you have, the longer it will take to calculate, but it was still doable within those time constraints that we had. I will now show some of the code that I used. This is for the first model, which is the naive Bayes classification algorithm. I used the CLAR package to run that algorithm. And then for SVM classifier, I used this package, the E1071 SVM. And then lastly, this is what I did for Model C, which is the AN classification algorithm. I used the neural net package. This is the output of the naive Bayes model. We get the accuracy of 56%. To evaluate the three algorithms, I used accuracy, RMSE, and MAE. So for accuracy, we want it to be as high as possible. And for RMSE and MAE, the lower one is going to be the winner. So from this, we don't really have a clear winner. The SVM model performed, I guess, the best on two of the measures, the accuracy and the MAE. So perhaps that's the best one to use. Surprisingly, the neural network had a very low accuracy compared to the other two. And the naive Bayes, although it had the highest accuracy, it actually also happened to have the highest RMSE and MAE. So I wouldn't call it a winner. I think I would choose SVM based on this type of evaluation. Validation, I use the k-fold cross-validation on a smaller sample in the interest of time. So I used the carrot package to train the different model types. And then I looked at the result. The ensemble model gave me the most trouble out of the whole project. The steps I took was using the train function from the carrot package to create a base model made up of three models, the naive Bayes, SVM radial, and MLP, and then training the models using the training data sets. The trouble I ran into was the carrot stack function from the carrot package does not work for multi-class problems. So perhaps if it wasn't a multi-class problem, if we're only predicting a binary variable, then this wouldn't be an issue, but this was something that I really struggled to debug in my code. So the lessons that I learned, there are so many from this project. I truly feel I learned a lot, but some of the key things that jump out at me are to check the variable types, whether it's continuous or categorical, and how many of them are in the data set, what really is the mix of the variables, and whether you can transform them before deciding on whether you will pursue a regression versus a categorization problem. I feel like I invested too much time formulating the regression problem before I made the switch to the categorization problem. And of course, normal distribution is very important assumption for regression. Make sure that all your variables can be at least transformed to reduce the skewness. But if that doesn't seem to be happening after you tried several transformation methods, then perhaps this is not the best problem, is to use the regression. And I also learned that the SVM algorithm can run a long time if the data set is large, or if there's a large number of features selected. It really works best with smaller data sets and a limited number of features. So even though I think it was still the winner among the three algorithms that I used, it definitely took longer than the rest of the algorithms to run. Not prohibitively long, but quite a bit of time compared to the other ones. I also learned that the neural network doesn't always have higher accuracy over other models. I was surprised by that because I really thought it would be the most accurate. In terms of accuracy, the naive Bayes and the SVM model performed better. And then lastly, but very importantly, the caret stack function with the caret package can handle multi-class problems. So either it has to not be a multi-class problem or don't use the caret stack function. So that concludes my project. Thank you for listening. Goodbye.